My name is Rob Lawrence. I'm a postdoc in Brenda Hope's lab at ASU, and I'm going to give a review of this paper, which is also the topic is also about algorithms used for data processing, and I'll say that this is not my area of expertise. I work in a microbiology lab, so I'm going to keep it brief. I guess we kind of need to anyway. So the title of the paper is High Resolution Structure of Viruses from Random Diffraction Snapshots. And the title I think is a little misleading because it's not, it's a theoretical paper. It's not something that's practically been done. But it's a discussion of how the collection of single particle diffraction data could be used to put together to produce higher resolution structures. And the reason why that's important is because this one. Okay, so because so far we've been pretty limited in terms of sorry, we just got a disconnection there. It's okay. So far we've been pretty limited in terms of gathering high resolution data from single particle diffraction. The Mimi virus, in terms of what's been done experimentally, the Mimi virus is probably the best example. There was this paper that just came out this year. There was a follow-up from the original Mimi virus paper back in 2011, and they did 3D image reconstructions of 3D diffraction patterns, and were able to do the reconstruction up to about 1,000. Or I guess I could say 125 nanometers, or 1250 angstroms if you're a crystallographer. And so that's about 1/3 the diameter of the particle. The Mimi virus itself is about 400 angstroms or 4,000 angstroms in diameter. So it's useful because it shows that it can be done in practice. But in terms of this being useful for the virus community or the biology community, we need much higher resolution to be able to say very much about the structure. And so a lot of the limitation for this is just in terms of how we're able to process the data, as well as being able to collect enough data to use. So traditionally, Bayesian approaches have been used for processing single particle data. I'm not sure if I'm pronouncing that right. Bayesian, thanks Nadia. Bayesian approaches. So these are some of the first approaches we've used, and it's a maximum likelihood approach. In general, it's an equation or an algorithm that collects, it uses past experience to make a future prediction, it's the problem with this is that it's limited by computational power. So the resolution that we can obtain using these type of methods is limited to about 1/10 the diameter of the particle that we're looking at. And so there's this equation that's put in this paper that diameter over resolution to the 8th power is a representation of the computational expense that's involved in doing this. And even though computation power is improved and increasing over time, we're still pretty limited in what we're able to do with this approach. Another thing that's discussed in this paper is the Shannon-Nyquist Theorem. So this is not specific to crystallography, but it's a theorem that is adapted in this paper to show how resolution is a function of the number of available elements that are in a point group, and that's defined by NG here, as well as the number of available snapshots. So the take-home message from this is that when you're dealing with a particle that's icosahedral, like a virus, it has orders of symmetry about it. Definitely a lot more than a protein would, and we can use this to our advantage when we're processing data to improve the resolution, because the number of available elements in the point group of a symmetric object, as that goes down, the resolution will go up, and it will also make it so that you don't need as many snapshots, so you don't have to collect as much data. So that's how, this equation is a representation of how we use the symmetry of something like an icosahedral virus to our advantage for processing data. So the whole objective of this paper is to use symmetry operations for the objects that we're looking at and combine those with manifold approaches for data analysis to process XFEL data to produce higher resolution reconstructions. And the manifold approach that they use is a diffusion-map algorithm. So so this is generated from eigenfunctions of Markov matrices to map coordinates of complex geometric structures. Basically, what that means is that when you have the diffraction of your object, we need to describe that in a geometric fashion. And the unknown here is what the eigenfunctions are. So what they propose doing in this paper is using Wigner D functions and correlating those with eigenfunctions in order to identify them. And this is the equation that's used to describe that. And here's a look at some of the data where they've done this in practice. So they use data from the PDB of the satellite tobacco necrosis virus, which I'll come back to in a minute, and mapped out the eigenvalue index for that and compared it to what you would get from an icosahedron that describes, or what Wigner D functions that describe an icosahedron, and they compare really well. So, so that's a demonstration of the utility of it. And here they take the Wigner D functions, and they have on these two axes. One is the negative value and the other is a positive value, and they map them against each other and then find eigenfunctions that correlate to those. And they found 13 different eigenfunctions that would correlate within the icosahedral space group parameters. And so then the next thing that they do is take those eigenfunctions and map them here on the coordinates from what I previously showed in the other slide. And this is used to identify the mixing angle. So 6 different mixing angles can be determined from the 6 degenerate pairs of the eigenfunctions and the other function that I mentioned. I'm just forgetting the name of Wigner D function. Thank you. Okay, so we need to have this theta sub n mixing angle value in order to predict, or in order to correlate the orientation of the diffraction that we measure. So, so this is one of the viruses that they used to do this with, the satellite tobacco necrosis virus that I mentioned earlier. So it's about 20 nanometers in diameter, or 200 angstroms if you're a crystallographer, and it's about as small as viruses get. You really don't see them much smaller than this. And so this was a good example because the resolution that they're shooting for with this work is 1/100th of the diameter of the particle. So having a particle that's 200 angstroms in diameter means that they can get a resolution up to 2 angstroms, and that puts us in the atomic range. 2 angstrom resolution can help us, or can enable us to see down to the atomic level of amino acids when we're looking at the protein structures. The other virus that they did work with was the Chlorella virus, and this is on the larger spectrum of viruses. It's 1900 angstroms in diameter, not quite as big as the Mimi virus. And here's a look at the data that they came out with doing this. So they did different photon energies from 0.5 to 7 keV, at least the satellite tobacco or satellite mosaic virus. And this is the number of photons that they were able to get. Of course, the lower the energy, the more photons per Shannon pixel. And And they did this at a collection angle of 30 degrees, and they used a beam diameter that was equal to the diameter of the virus. And so here's a look at a map of the diffraction volume. This is the exact diffraction volume that they would have expected, and then these two are what they recovered. The first one is without the noise, and the second one is with Poisson noise added in there. And so the take-home message from this is that the algorithm that they developed is pretty robust to noise. There doesn't seem to be a huge difference there between the two. And so in theory, the approach should be comparable to the resolution you get with cryo-EM. I kind of raised the question, but what about big viruses? Because it seems to be a function of the size of the virus. So I'm not sure what the answer to that is. It also doesn't provide phase information, and they said in their paper that in order to do this with experimental data, they needed improved XFEL virus data sets. Siobhan mentioned to me that they have already tried this or are in the process of doing so. So I haven't had a chance to look that up yet, but anyway, that's about all I've got for you. Do you have any questions?
Thank you, Rob.